Hey, greetings, peeps. Welcome to Tracker. And what I have here is a recording that we did in period one, a recording of the tennis ball drop. And this is from Pomerleau's window. So we were trying to figure out the acceleration due to gravity and compare three different masses. And so what I'm going to show you, though, are the cooler features of Tracker that we didn't get into yet in class, but we will soon. Okay, so the first thing I want to do actually is just find the boundaries of the event in time. So I'm just kind of looking, and about 2/3 of the way of this particular clip, there's the event, the drop. So what I'm going to try to do is zoom in so that we can see the drop occur. All right, and right here we see the hand open, and I think it's open here because we can see that it's tightly clasped here, and over here it's open. So we're going to start with the tight clasp, and that's V naught equals 0 right there. So what we're going to do is take this triangle on the left that's going to begin our start frame. We go to slider 193. That is frame 193. What we're going to do is change the display here. We want to set the time so that this is 0. So our time origin T naught is going to be at frame 193, and we see that this is now 0 over here, like it should be. So we want to find the end as well, and that is when the ball actually hits the ground. Okay, so we move and the ball hits the ground. Oh, bounced over there, like so. And so we see the ball on the ground. And with the other black triangle, we're going to set end frame to slider 226. And so that is the boundary for our event. And over here, you'll notice that the time is 1.1 seconds. Now, I think when we did this in class, we got 1.07. And I think what we did was I probably started a frame later. I looked closely, and up here, we see that the ball was actually falling one frame earlier. So here we go. That's something that we've been able to establish so far. We can use this 1.1 seconds and the known height to calculate the acceleration of gravity and also the final velocity. Not bad, but we can do better. We can actually have Tracker do a lot of the analysis for us. So here we go. Tracker doesn't know what the height is, even though we did it 5.4 meters. So we have to tell it what the scale is. And the way we do that is by going over here and create a calibration tool, and we will create a new calibration stick. And there's the stick in blue over here, you see? And so what I want to do actually is stretch that stick out so that it is the full length of the drop. And I'm going to make sure that its beginning and end is, well, let's see, at the top here where the brick is, right there. And the bottom where the ball lands, and that's about here. We'll zoom in to make sure. And we want to tell Tracker that that stick is actually 5.4 meters. Okay, so that should be pretty good. This thing, we want to make sure the stick is also parallel with the camera and the drop, so that we see that the bricks mortar lines are in the same. It's parallel to this line over here, and so we're going to change this to, well, 5.4 meters like that, and we get 5.4 over there. All right, so it looks pretty good. I'm going to turn that off. The next thing we need to do is to establish our coordinate system. So I'm going to go back over here and right at the beginning of the ball, and I click this over here, show or hide coordinate axes. Okay, so we see one of those axes. Now we see the crosshairs, and I want to take the center of the crosshairs and bring them over to the center of the ball, like this. So that is our origin, okay? And this thing also, it looks like it's actually, its orientation is pretty good, but if we need to adjust it, we could always move this up and down so that the angle changes. So I want that angle, again, to be parallel with the drop. And so we're looking at the mortar over here, and it looks like it's pretty good. It looks like everything is parallel like it should be. So now we've got the two things. We've got our calibration stick telling the height, which scales the analysis for Tracker, and then the coordinate system. And I'll turn that off as well. Next, what we're going to do is go to track, new point mass. We're going to pretend this ball is basically a point, and it kind of represents one in its fall. And so we got mass A over here, okay? And what I'm going to do is start shift clicking the ball, and what you'll see is that we're going to create some points for this ball. All right, so we got auto step, which is good, and we got it visible. All right, and now when I hit shift, my cursor turns into this square kind of thing, and then what we see is that the frame will advance and move. And so what I'm doing here is creating little tracker dots, kind of like what Phineas does with his poops. Well, we're doing here with what will be diamonds later on. And what I'm trying to do pretty much is just go for the center of the ball. Now the ball begins to turn into a streak, as we notice, and I'm just going to try to choose around the center of the ball, hoping that that's you know, where it is. The thing becomes a streak because it's moving so quickly relative to the aperture setting of the camera that it kind of blurs. So oops, let's get rid of that one. Delete. Oh, let's see. Can I get rid of that one? Yep. And so we just make our best possible guess as to where the ball would be until we get to the end. And this doesn't take that long to do by hand. Well, I'll show you an auto mechanism called Auto Tracker, surprisingly. And but here the event is about 1.1 seconds. So that's 1.1 times 30. So 33 frames ought to do it. And we're at 32, and guess what? 33rd frame, and we're down here. Awesome. So now we kind of see the trail, noting that with acceleration, the spacing in between each of these diamonds that represents the position of the ball increases. That's due to the acceleration. Now we kind of expected that pattern, but the thing is that we can do much better. And here's what I mean. Tracker has these awesome features to take that data and make it into a graph. Now this is a funny graph because it doesn't mean a whole lot since we're plotting the x-axis over here, and that's not what we want. The coordinate system that we established before, one over here, right? That coordinate system thinks that the x direction is horizontal, and that's left and right, and the y direction is up and down. So actually we're looking at the y would be the preferable axis to look at the fall of gravity. So I'm going to switch this over here to y, and look at that. We get this beautiful looking parabola-like thing like we'd expect. That's pretty cool. This is a d versus t graph in the y direction. So what I'm going to do is take a look at it a little bit closer. With the data tool, we can analyze this whole thing. And I'll show you a couple ways that will allow us to actually look at the acceleration anyway. And we got some tools here in Analyze, and I'd like to show you one. We have slope in the measure, kind of like in Logger Pro. This slope, and by the way down here where it's yellow, gives us that indication, and it does it here in such a way we can see the slope is increasing, and that's good because that means the velocity is increasing as well. Alright, so I'm going to go back to this Analyze feature here and select Curve Fits, and the one that I want actually is not a line but a parabola because that's what this shape is. Okay, so you'll notice over here that we have this equation that looks a lot like the third one on your smileys for the equations of motion, which is d equals v naught times t times 1/2 at squared. Okay, this is the quadratic equation over here, and in front of t squared we know that should be 1/2 a. So this big A, which is a coefficient, is reading -5. So if we double that, it's about -10.08, which is pretty good. To the established value of 9.8 is what we're looking for, the established value of, or accepted value of acceleration due to gravity, 9.8 meters per second squared. So this is giving us the value of acceleration from this d versus t graph, which is a very cool thing. But we can also get it from, of course, velocity versus time. How do we do that? Okay, well, I'm going to take this window, close it, and I can select from a whole bunch of different things over here. Instead of y position or y component, I can go to vy, so velocity for the y component, and we see that it looks like this, which is pretty much a straight line. Let's take a better look at it in the data tool. All right, actually got two graphs here. Let's see if I can turn some of this off like that. Okay, so yeah, this is the graph over here. Now we got a couple of funky little points where it got fuzzy. I might not have chosen perfectly in the center, but basically this thing is a straight line. And so instead of choosing parabola, I will choose line. And what I get is this. I get a line with this coefficient a represents the slope. This is y equals mx plus b. And the slope, capital A here, is -1 times 10 to the first. So it's e to the first power. This is -10, which is darn close to the -9.8 meters per second squared. So this slope here is great. This is telling us what the acceleration is also. So we have a couple of looks at how to get it. And so that's what we're going to do. We're going to use Tracker to analyze other videos with more complex motion that are in 2 dimensions. We're going to look at projectile motion. And but we're going to try this and see what we can do for the other 2 balls that were dropped, and to see if we get the same acceleration, somewhere around 10 or 9.8 in that range for the experiment, and at least to tell if they've dropped at the same rate. All right, so that's a look at Tracker and the funky tools. I'm going to show you in another short clip the auto feature because it's pretty neat, but even in plotting these points by hand, we get this result pretty quickly, although apparently I deleted number 22, but it looks like we could extrapolate in between and did pretty well. So that's what it is. That's how Tracker can be used. And we're going to be using it quite a bit in the next few weeks. So hope you dig it. That's what it is. Morad out.